All right, let's talk about hydrogen. You've heard the hype, right? It's supposed to be the clean fuel of the future, the silver bullet for powering our world. And, when you just look at the science of it, the promise seems, well, almost too good to be true. And hey, this isn't some new fad. For decades, we've been dreaming about a world running on the most abundant element in the entire universe. And the dream is just so elegant. You take hydrogen, you use its energy, and the only thing that comes out the other end is water. Simple, clean, but what really makes it so special? Well, here's the kicker. It's all about energy density. By weight, hydrogen packs a massive punch. We're talking nearly 3 times more energy than gasoline. Just think about that for a second. A fuel that powerful, and the only exhaust is pure, clean water? I mean, it really does sound like the perfect fuel, doesn't it? But, of course, there's a catch. There's always a catch, right? The big, kind of sort of secret of the whole hydrogen economy is this. The fuel itself is always clean when you use it. The real environmental cost, it's all hitting in how we make it. And that, my friends, is where the story gets a whole lot more complicated. So to make sense of all this, the industry came up with a pretty clever system, a color code. Each color tells you exactly where that hydrogen came from. So let's dive in and explore this hydrogen rainbow, starting with the colors you'll see the most. Okay, first up, gray and blue hydrogen. And here's the really surprising part, the part most people don't know. The vast majority of hydrogen made today, like well over 90% of it, is made using these two methods. And both of them are tied directly to the fossil fuel industry. The absolute workhorse of the industry is a process called steam methane reforming, or SMR. It's pretty straightforward, really. You take natural gas, which is mostly methane, you mix it with steam, crank up the heat and pressure, and boom, you split off the hydrogen. It's really efficient at what it does, but there's a huge downside. It leaves behind a massive amount of CO2. And this is where we hit a fork in the road. It all depends on what you do with that CO2. If you just let it vent straight into the atmosphere, well, that's gray hydrogen. It's the cheapest, but it's also the dirtiest. But if you capture that CO2 and you store it permanently underground, that's a process called carbon capture and storage, then it becomes blue hydrogen. It's definitely a cleaner option, but you gotta remember, it still starts with natural gas. So you might be asking, okay, but what if we could just not use fossil fuels at all? Great question. And that brings us to the color that gets all the headlines, green hydrogen. This is the one that truly lives up to that clean fuel promise. The process here is just beautifully simple. It's called electrolysis. You just run electricity through water, and it splits the H2O into its two basic parts, pure hydrogen and pure oxygen. You notice what's missing there? Carbon. There are 0 carbon atoms anywhere in that equation, so you literally can't make CO2. Now, the one catch, and it's a big one, is that the electricity has to come from a renewable source, like wind or solar. That's what makes it green. Okay, so if green hydrogen is so perfect, why isn't everything running on it already? The answer, as it so often is, comes down to one thing: cost. Right now, the technology for the electrolyzers and just the sheer amount of renewable energy you need, well, it makes it a whole lot more expensive than the old fossil fuel methods. And closing that price gap, that is the #1 challenge. But the rainbow doesn't just stop at green. There's a newer, really innovative player entering the game that takes a completely different approach. And its name is turquoise hydrogen. Okay, now this is where things get really clever. Turquoise, like its gray and blue cousins, starts with methane, but the chemistry is totally different. Instead of using steam, you use incredibly intense heat in a chamber with no oxygen. The process is called methane pyrolysis, pyro meaning fire, and lysis meaning to split. It literally cracks the methane molecule apart, giving you hydrogen gas and something totally unexpected. And this is the absolute game changer for turquoise. That something else isn't a gas like CO2, it's solid carbon. And we're not talking about waste here. This is a valuable industrial material called carbon black. It's used to make everything from car tires to printer ink to batteries. So think about it. Instead of paying money to bury a waste product, you're creating a second product you can actually sell. That could completely flip the economics on its head. All right, so we've got all these different ways to make hydrogen. But once you have it, it doesn't matter if it's gray, blue, green, or turquoise. Every single color on that spectrum runs into the exact same fundamental challenges of physics and chemistry. First up, storage. This is a huge one. Hydrogen is the lightest element in the universe, which means it takes up a ton of space. To shrink it down and store it as a liquid, you have to get it mind-bogglingly cold. We're talking minus 253 degrees Celsius. To put that in perspective, that is colder than the surface of Pluto. And getting something that cold takes a massive amount of energy and some seriously expensive specialized gear. And then there's safety. Look, hydrogen is flammable. It takes over 15 times less energy to ignite than the natural gas we use today. That is an incredibly low threshold for a spark. And what that means is that designing pipelines, tanks, and fueling stations that are 100% safe, well, that's a massive engineering puzzle that we absolutely have to solve. So, where does that leave us? We're kind of staring at a choice, right? We've got the established but dirty method, the clean but super expensive one, and this really cool, innovative but still unproven path. So, what color is our energy future going to be? Let's just lay it all out one more time, nice and clear. Think of gray hydrogen as our high-carbon legacy. Blue is a potential bridge to something better, but it's a bridge that's still built on fossil fuels. And then you have green and turquoise. They represent two totally different roads to a near-zero carbon future, but as we've seen, each one has its own mountain to climb. And this brings us to a really crucial point. Maybe, just maybe, asking which single color is the best is the wrong question entirely. The future probably isn't going to be one color. It's going to be a mosaic. You can imagine a world where we use blue hydrogen to start cleaning up heavy industry right now, while we wait for green hydrogen to get cheaper for our cars and our power grid. And turquoise? It could become a powerhouse in certain regions, turning a natural gas supply into both clean fuel and valuable materials. So when you boil it all down, the real challenge isn't about picking one winning color and betting everything on it. No, it's about learning how to use the entire rando. It's about building the tech and the infrastructure to support a hydrogen economy that's flexible, diverse, and truly clean. The palette is right here in front of us. The only question left is, are we ready to start painting?